uh, remedies. Each bio-inspired medical innovations, the natural world continues to guide breakthroughs in health and well-being. So, for the today's webinar, it is our absolute honor to welcome our distinguished guest speaker, Dr. Angelo Karunarathne. Let me introduce him to you all. Dr. Angelo Karunarathne is a biomedical engineer and research officer at Swansea University, UK, with a passion for translating cutting-edge science into real-world impact. With a PhD from Queen Mary University in London, his expertise spans biomaterials, biomechanics, and wearable health technologies. Dr. Angelo has led innovations at the intersection of nature-inspired design, engineering, and human health, developing solutions ranging from compression devices for elderly care to advanced diagnostic wearables. He also lectures internationally and consults on health tech strategy, bridging academia, industry, and global innovation ecosystems. So now let's get inspired, let's get curious, and let's rethink medicine the way nature intended. Dr. Angelo, the virtual stage is all yours. Sir, over to you, sir.
Thank you. Thank you, Sunimali. Hope you all can hear me.
Yes, sir, we can hear you clearly.
Right, great. Let me get my screens up. Right, hope you all can see my screen as well. Sunimali, can you tell me whether you can see my screen?
Yes, sir, we can see your screen.
Okay, great.
It's all clear.
Right. Okay, thank you. So, hello everyone. Most of you, I think it will be a good evening for you all. And thank you so much for joining for this Nature Talk series. It is a real pleasure to part of the Nature Talk series. What a fantastic platform to explore beautiful interaction between the natural world and the world of medicine. Growing up in Sri Lanka surrounded by tropical biodiversity, I always fascinated by the intricate ways nature solves problems. But it wasn't until I entered the world of biomedical engineering, working with scaffolds, soft robotics, and wearable tech, that I began to appreciate just how deeply nature inspires innovation in medicine. So, today I want to take you on a journey from the veins of a leaf to natural bridges in the human spine. We will explore how natural principles are embedded in some of the most cutting edge medical technologies. And don't worry, this is not going to be an academic lecture. We are going to talk about real patients, real research, and real impact. I'll share insights from my own research, wearable cooling garments to implantable scaffold to some unexpected, inspiring animal learnings, from turtles to camels to parasites. So let's dive in. So, what if the next medical breakthrough came from a leaf or a nerve? Have you ever noticed how some of the most efficient, elegant designs in science already exist in nature? Nature has had about billion years of research and development, trial and error and optimization. Every plant, every animal, every microscopic organism has had to solve survival problem. How to regulate temperature, how to repair damage, how to transmit signals, how to defend against threats. And these are the exact challenges we face in our daily life as well as in the medicine as an industry. When I was working on a passive cooling technology for elderly patients, we were stuck. We needed a material that could help regulate temperature without needing power, because elderly people, they don't want to carry batteries and power sources with them, and also they don't even want to charge their devices. They want something that works lifetime. without that much hassle. And the solution, it came from camel nasal passage. More on that later. What I love most is the nature doesn't waste. Everything is multifunctional. Spider's silk isn't just strong, it's also elastic, biodegradable, and responsive to humidity. Now, if you think about the lotus leaf, isn't just waterproof, it also self-cleans. So why nature? Because it offers sustainable, adaptive, intelligent design solutions without reinventing the wheel. So in this talk, I'll show you how we can borrow some of these solutions to improve our health outcomes, enhance medical devices, and even transform how we think about healing. So, why nature matters in medicine? That's the question we are going to ask, right? Now, you can see this is a split slide where on the one side, what you can see is a leaf. On the other side, also on the same side, you can see a leaf and a turtle shell. On the other side, you can see a stent and a implantable orthopedic implant device. If I correctly said, is a hip replacement device. Right. Now, nature, like I said in the earlier slide, the R&D has happened for billion years. To be exact, it's 3.8 billion years of research and development, right? Because they also had a survival game. So let's start with the leaf vein analogy. In our research into vascular grafts, we saw that many artificial vessels failed because they didn't allow for distributed flow. Leaf veins taught us that branching hierarchies can avoid blockage, maintain flow under pressure, and enable redundancy, exactly what we want in a stent. Now, if you think about the turtle shell, it's not just armor, it's layered. I'm going to talk about more in the next few slides, but just to complete the lecture slide, hard outer shell, softer inner core, and then bone matrix underneath. So it's a layered structure. Um, this has inspired multi-layered orthopedic braces and even body armor for military use, where comfort, flexibility, and impact resistance all needs to coexist. This is what excites me. The idea that a turtle evolved over millions of years with structure that can help protect humans recovering from trauma or even soldiers on the front lines. Nature is not just a teacher, right? It's an engineer with a billion years of head start. Right. Now let's really look at how to think nature. Now, what is this biomimicry process is, right? We are talking about biomimicry process. So let's talk about how we actually go from observing nature to designing something useful. I think most of you are students here, join this lecture. I would like you to start thinking about your projects also in this form. You identify, you interpret nature's function in this particular scenario, and you discover, emulate, and evaluate. Let me walk through an example. When we were developing passive cooling garments for infants, essentially breathable pre-swaddle, we didn't start with the question, how do we make a better swaddle? That would be the question, right? But no, we ask, how does nature keep organisms cool without active systems? So we identify thermal regulation in camels, which I'm going to talk about next in few next slides. It's interpreted their nasal heat exchange system, discovered how their fur and skin layers work in tandem, and then emulated it using layered textiles and phase changing materials. Finally, we evaluated the performance in a lab. Does it regulate microclimate temperature effectively? This process applies across all disciplines. When you see a leaf's vein structure, think not just of beauty, right? But of flow optimization, how it's optimized the flow. Finally, we evaluated the performance in a lab. And then from that, we validated the entire process. So that's how the stent were redesigned as well, mimicking the redundancy and benching the nature's vascular system. Nature doesn't inspire shapes, it inspires the system thinking. So I want you to really think about when you are looking into a project, apply these 5 stages. So let's really deep dive into this lotus leaf. I've been talking about that in the previous few slides, right? Right. Now, I told you about the self cleaning, how they do the self cleaning. Now, you can see in this slide, it's a split slide. One side, you can see the lotus leaf surface, which was taken with a scanning electron microscope image. And on the other side, you can see a fabric surface. So let's have a look at how we use that inspiration that we are getting from the lotus leaf into this fabric. So if you ever seen the water roll off a lotus leaf, you know what I mean. It's watching liquid mercury dance, right? What's happening here is superhydrophobic effect, microscopic bumps and nanostructures that repel water and dirt. That's what you see on this surface. This is more than a cool party trick. It's a revolution of material science. In our wearable tech projects, like wristbands, we develop few wristbands for different brands, and cooling garments, we took this principle and applied to our smart textiles. We have developed monofilament yarn based breathable layers, very much similar to what you see on the lotus leaf, by mimicking the microstructure of the lotus. We created fabrics that don't trap sweat, are easy to clean, and allow airflow. Perfect for athletes, elderly patients, children in warm climates. And from a healthcare perspective, think about wound dressings that don't retain fluids and reduce infection risk, or catheters that don't get biofilm buildup. That's bioinspiration. This is what we call bioinspiration. Observing how a plant stays clean in a muddy pond and translated that into real clinical value. So let's look at another project that I'm currently working with University of Moratuwa and Imperial College in collaboration. So now here, what is fascinating interaction of nature and biodesign, biomedical design. One of my favorite example, right? Take a look at the honeycomb structure, what you see on this in the middle, right? That is a honeycomb structure. So it's more than just a marvel of insect architecture. The hexagonal structure, geometry it uses is one of the most efficient structures in nature. High strength, low material usage, and lot of internal space for beehive to store in, right? That's what the honeycomb structure is used in nature. So we brought this structure into biomedical engineering. We borrow the same geometry for bone scaffolds. What you can see on the right-hand side picture, left-hand side um, image, where the doctor is actually implanting a scaffold into a broken bone into a patient leg, right? So we look at that porous structure. It has to allow nutrients and cells to move through it. At the same time, it has to give that structural support during the healing process. So in this case, the 3D printed or fabricated these honeycomb-like scaffold, they go into large bone defects. These bio-inspired scaffolds support healing by 3 ways: mimicking the bone trabeculae architecture, supporting mechanical load while still being lightweight, and facilitating the vascular ingrowth and tissue regeneration. You will notice here we show a surgical context. This is not a fiction. These designs have moved from lab bench to surgical trials. So we are learning from bees to help bone heal, right? So I want to inspire you by showcasing some of the real laboratory work that we are currently doing at University of Moratuwa. So here you can see a mechanical setup. It's not that we design the scaffold and we can simply put it in the patient's leg. We have to do a lot of testing beforehand. So my PhD MPhil student, Nisha, she's working on this project, taking these scaffolds from Imperial College London, and they are mounting in a test rig to apply mechanical forces to see whether it can sustain the load conditions that experience inside a human leg. So we simulate the real life conditions by combining the cadaveric bone, hybrid scaffold, and external fixators. And we mount the entire thing in a universal testing machine, as you see on the picture. And when the patient is walking, what sort of loading conditions are happening, we have studied from the literature and we apply that in this study. So what we can capture, how the scaffold deform, and when and where failure occurs, how it integrates with the bone and fixator system. We also mount micro cameras closely to monitor the failure zones, because what you see visually tells you a lot about the material tissue interaction. Why this is important? Because we want to replace damaged bone. We need to be sure the scaffold perform not just biologically, but mechanically too. And real bones don't just face one-time load, it experience fatigue, cycles, bending, torsion. So this is where biomechanics meets regenerative medicine. So not only that, we can't stop there, right? But we also need to look at how bone behave inside the human body. Now, to do that, we can't get a person, living person, and put a scaffold in there and image it. At the moment, the technology is not uh, developed to that level. So we had to do some finite element analysis. So this is where the finite element analysis comes in. Using a software like Abacus, we can predict how our honeycomb scaffold will behave before we even manufacture them. Each of these images represent a step in that process. The color map shows the stress distribution and the scaffold. The observe how different layers and direction behave under compression. We simulate failure under different loads and orientation. This is especially valuable when we exploring new designs or trying optimize the mechanical properties. So we don't want to stop there. After we design this structure, after we get a validated honeycomb structure or the material properties, then we want to simulate the cell ingrowth as well. How this mechanical loading, how this honeycomb structure um, promote cell growth, vascular growth, and bone development within the scaffold. So this is a small video. Let me see whether it works. Yeah. So you can see this is how when the load is applied, it's actually changes its stress levels. And you can see where you get the highest stress levels, where you need to optimize the material properties and etc. Right. Okay. So the next one of my favorite, we use this design in multiple scenarios, right? So nature's blueprint in bracing and armor, right? Let's zoom into that multi-layered structure that I explained to you earlier. In the turtle shell, you can see the tough keratin structure outside, then the porous structure, and then finally you have a softer elastic underlayer. This hard, soft, hard configuration gives the turtle the ability to withstand tremendous external forces while protecting the internal organs. In orthopedic engineering, we applied this very idea in brace design and exo armors. Take braces for spinal injuries, for example. Patient needs support, but also mobility, the comfort, because they need to move around, they need to walk, they need to sleep, have naps. So by layering the rigid support shell over softer viscoelastic form and skin-friendly lines, we mimic the turtle's strategy of defend, cushion, and adapt. When I was involved in designing wearable protection in the industrial workers and even defense prototypes, we mimic this biomimetic sandwiching to absorb shocks, reduce fatigue, and increase compliance. Because let's face it, if the brace is uncomfortable, nobody gonna wear it. And especially we are talking about patients, they don't want to be uncomfortable when they have a problem anyway to suffer with. So nature understands that form must follow function and comfort. And it's not just physical, this biomimicry gives us design confidence. If evolution has already tested this millions of years, there's good chance it works. So next, I'm going to talk about another interesting uh, inspiration from the nature, which is a camel thermal regulation, right? Camels live in brutal heat, right? You know, they live in deserts. Yes, they maintain core temperature remarkably well. It's not magic, it's physics, anatomy, and evolution. Inside their nasal passage, there's a complex maze, turbinated bones that create massive surface area to cool and condense moisture. Their fur acts like as an insulating shield, tapping air pockets and minimizing the heat transfer. We use this exact principle when developing passive cooling garments, particularly for newborn soddles, elderly population, and especially tropical regions like Sri Lanka. Instead of relying on battery-powered fans or gel that wear off, we explored phase-changing materials, specifically talking phase-changing yarns and monofilament structures that regulates the microclimate. The idea mimicked the camel's ability to trap coolness close to the body and delay heat gain, especially during the nap time or prolonged bed rest. This isn't theory. We have tested prototypes in our lab and with real users, and the outcomes were encouraging: better skin comfort, reduced sweat, higher compliance. It's one of my favorite examples where a desert animal helped us rethink thermal comfort in human textiles. Then the bionic limbs with sensory feedback. Now, restoring touch with brain control prosthetics. Now, here we step into frontier of neural engineering. This image might look very futuristic, right? What you see, but it's already happening. A patient with a prosthetic arm is not just moving it with their mind, it's they are feeling with it as well. This is made possible through neural feedback loops, where sensors in the fingertips send signal back to the brain via peripheral nerves. It's not just about grasping, it's about reclaiming the sensation. So they can feel what's happening, what they touch, whether it's the texture, whether it's a soft, whether the temperature, or even the pain. In our research collaboration, especially during my time at Imperial and now at Swansea, we are beginning to explore these interfaces between the soft materials and neural control systems. One area I am particularly excited about is biodegradable electrodes, tiny flexible devices that dissolve over time, reducing the need for surgical removal. When you think about it, this is full circle story. We are not just mimicking the structure of limbs, we are mimicking their function and intelligence. Imagine the dignity that returns to someone who can once again feel the warmth of a loved one's hand. That's what this is about. There's another quite futuristic idea that combines this tissue engineering. So, growing organs. Now, let's shift from machine to regeneration. This is the Ori Nova ear. What's remarkable is just it's shaped like a human ear. It's that is made from patients' own living cells. This is how it works. Cells are harvested, and you cultivate the cells outside the human body. Then you mix into bio ink. Often it has to be collagen based because here the cartilage is collagen based. And then printed using a 3D printer to match the exact shape of the person's ear. And why this is revolutionary? Because it solves three massive problems. Now, one of these implanting issue, when you implant materials, they reject human body because human body think this is a stranger, right? So they try to reject. So it's avoid the rejection risk because it uses patient's own cells. Then aesthetics and symmetry, particularly in critical and pediatric cases like microtia. Then long-term integration, it grows and adapts with the body. So these are the three areas. And during my PhD, I explored this how tissue microstructure correlates with mechanical performance. That research laid the groundwork and understanding how important scaffold architecture is not just chemically but structurally to guide cells in forming new tissue. This inspiration here again, the nature. Think of ear cartilage, flexible yet sturdy. Think of plant scaffold, which guide nutritions. We mimic both. Now imagine this tech applies to nose, trachea, even kidneys. We are witnessing a shift from prosthetics to biointegrated living replacements. It's no longer science fiction, actually, it's science translation. Then, if you really look at another example of this neural technique, brain neural technique, this might be one of the most emotional breakthroughs in recent years. Now, this particular scenario, real scenario, who actually got the spinal injury, left a man paralyzed for 10 years. A brain spine interface helped him to walk again. What does that mean? Essentially, sensors implanted in his brain picked up movement intentions. So he is thinking in his brain that I want to move my body, right? Now the paralyzed person always think that he want to move, but his body is not moving, right? That's what we call paralyzed. These were transmitted wirelessly to simulators in his spinal cord, bypassing the damaged area internally, entirely. A digital neural bridge, if you will. Now, this may not seem directly related to nature, but let me challenge that. Nature has always relied on redundancy and rerouting. Think of plants redirecting growth after damage. Think of salamanders regenerating their limbs with full nerve function. We are not just copying the nature's forms, we are learning from nature's resilience strategy. I have been fortunate to work on early stage projects that explore how mechanical loading, electrical signals, and neural cues combine to support healing after injury. This slide brings all of that together. And the best part is the patient didn't just move, he relearned, and neuroplasticity, a concept nature has built into us from birth. This is a mind control game, right? Interesting study that I actually learned this particular scenario in the previous biomimicry lecture, biomimicry conference in, I think it was in July last year. So this is the wildest part of the talk, literally. This is Ochiodriceps is a parasitic fungus that invades the body of an ant, takes over the nervous system, and controls its movement, and leads to a location optimal for the fungus to grow and reproduce. It is brutal, right? When you think about it, you actually play with your mind, and remarkably sophisticated as well. From a biomedical perspective, it shows us that neuromuscular control can be hijacked, not just with wires and machines, but with biochemicals. This is an inspired research into neuromodulation therapies and even biologically guided robotics. Imagine microbots that can infiltrate tissue, respond to pH, or direct themselves towards inflammation zones. Not far fetched, where you consider how fungi do it with zero electronics. During recent collaboration, we discussed how to rebuild microstimulators that respond to internal cues, oxygen levels, stiffness changes, or even inflammatory markers, much like fungi reacts to host conditions. So while this fungus terrifies ants, it fascinates the scientists. It teaches us the biology at its extremes, hold the blueprint for behavioral engineering. Now, this is another interesting case. I always remember when I see this slide, I the this the childhood cartoon, right? So parasite that shape our minds. Let's take mind control a step further into our own species. Now, this is called Toxoplasma gondii. It is a parasite that lives in cats but requires rodent hosts to complete its life cycle. Here is the twist. When a mouse gets infected, its behavior changes. It loses its fear of cats. Sometimes it's even attracted to them, as if nature has built a suicide switch. It's like a suicide switch, right? Because now rats are not any, they reduce fear, they increase risk taking, right? Impulsivity, personality shifts, what I mentioned on this slide next to the image. Do you increase these things with with this parasite? Now, it doesn't stop there. Human can also carry this parasite. Around 30% of the global population does. And emerging studies show it may influence risk taking, impulsivity, even mental health conditions like schizophrenia. Some traits observe lowered inhibition, altered reaction times, even subtle personality changes like increased warmth or suspicion depending on gender. So, why include this in a biomimicry talk? Because it opened the door to biomedical diagnostics, especially neuropsychiatry. So imagine early detection of parasitic influence on the brain using non-invasive biosensing, or creating targeted therapies that prevent this behavioral drift. In one of our clinical pilot study, we considered how these biochemical markers and behavior analysis could be paired using wearable technology, measuring stress, motion, and microbehavioral shifts over time. This is where biobehavior meets biosensing, and we owe that insight to a cat and a mouse. Next one, I'm going to talk about something that you have seen, I'm guessing. A lot of biological tools, engineering tools, civil engineering tools are made using this particular bio-inspiration, right? Carl Gang's legendary morphologies documented how these animals move through soil and with minimal energy loss. Their secret is segmented. You can see on this diagram, flexible muscular waves of motion. This inspired soft robotics, tools that don't have rigid hinges but flow like muscle. And we have applied that this directly to catheters, colonoscopy, and neurosurgical instrument devices that must move gently, precisely through the body's winding internal landscape. You may have seen videos of octopus arm, robots, snake-like endoscopes that maneuver without causing tissue trauma. The engineering behind these devices is built on nature's kinematics, and snakes are one of the most perfect examples. In my own work in orthopedic biomechanics, I've looked at how soft and hard tissues interfaces respond under dynamic load. These soft robotics tools are perfect for applications like spinal navigation and interventional surgeries, where flexibility and precision are everything. And when you overlay this with artificial intelligence, pathfinding algorithms, you start to develop tools that aren't just flexible, they are intelligent. So from snakes to slither, we are revolutionizing how we move inside the body. So what else? Just the interest of time, um, I just want to here capture three different areas also for you to have a look at three different animal types that we can learn from. We just scratch the surface. There are many more that you can get as different examples. Now, gecko adhesive, we use this in our wearable technology space, textile space, and also in the medical industry. We are now using this dry adhesive inspired by gecko feet in surgical settings, allowing us to create glue-free, residue-free fixation methods like stick and release cleanly. Then spider silk sutures. Ongoing trials are now using synthetic spider silk to create ultra-thin, strong sutures that dissolve without triggering inflammation, ideal for neural and vascular repairs. Then octopus arm robotics, not science fiction anymore. Now we have tentacle-like surgical instruments that bend and conform, assessing hard to reach place with minimal invasiveness. And there are more. You can think about butterfly wings, guiding anti-reflective coatings, shark skin, inspiring antibacterial surfaces in ICUs. Now, at Swansea, some of the research also explored using biopattern surfaces for wound healing, mimicking the leaf ventation and the bone trabeculae to optimize fluid flow and nutrition diffusion. This is where biomimicry become biomedicine. The future is not about copying nature, it's about collaborating with it. So just before my last slide, we been talking about forest to hospital, right? Lab to life. Today, I was telling Sandeepa that I decided to have my slides very greenery, very nature inspired slides, and sitting in a lab to give the other part of the life, right? So now let's take a moment to zoom out and reflect what we discuss. The forest, an ancient, chaotic, yes, profoundly intelligent system, what you see on the image. On the other hand, a hospital, structured, sterilized, and filled with cutting edge tools. So the question is, what connects them? Now we know. As researchers, clinicians, designers, we serve as the bridge between these two worlds. This transition image, nature fading into a medical world, is more an metaphor. It's literally where I've lived. In my own career, I moved between microscopy labs, studying bone nanostructure, design studios, creating wearable devices, to clinical trials with aging population. Each time, I saw that biomedical solutions weren't just about precision, they were about harmony, harmony between soft and hard tissues, between internal cues and external designs, between biological inspiration and engineering execution. This slide is a reminder. If we want to build the future of medicine, modern medicine, we need to start by listening to nature. So, with that, that brings to us an end. I hope this journey of lab to clinic, nature to the clinic, inspired you, gave you some inspirational ideas that you can think about when you are working in a project. What are the different steps? How nature think? Maybe a memory, an idea, even a challenge to think differently. We live in a time when engineering meets biology and curiosity meets impact. Let's keep the conversation going. I'll happy to take any questions if you have. If you want to connect with me, you can connect with me on LinkedIn or any of these email addresses or anything for collaborative research project. Thank you, Sunimali. I'm passing it over to you to see whether there is any questions from the audience.
Yes, thank you so much, sir. So the audience, do you have any questions? So I can give you time for the audience to ask any questions.
Yeah.
Um, Seems like there's no questions from the audience, sir. So
Even if
let's
they can,
this.
they might, if they want to put it on the chat. I don't know whether the chat is available for people to ask any questions. But anyway, yeah, go ahead. You were about to say something.
Yes. So then we can wrap up this session. And uh, first of all, I have to give a big thank to you, sir, Dr. Angelo Karunarathne, for this inspiring session and this very informative and knowledgeable session that we got to know many things about biomimicry and its applications on bioengineering and many other things, and what the world have done and what they're planning to do, and new research topics and areas. And dear sir, thank you so much. And the audience also, thank you so much for um, attending this valuable session. And I've got some announcements to make. So I guess you all can see my video, the screen. And since we are conducting these Nature Talks sessions, the talk series with regards to our Biometry 2025 conference, I have little announcements to make that we have planned to organize an exhibition with regards with respect to the biomimicry conference. So the two main exhibition themes will be the ecomorph and the morphoware. So this ecomorph exhibition is mainly targeting on biomimicry innovation showcases. So the themes are structural design innovations, functional product prototypes, circular and regenerative systems, bio-inspired materials and services. Yes, there was an interruption. Mm. Sorry for the interruption. And I was talking about the exhibition that we have planned to conduct on this biomimicry conference day on 26th of September. And also we have the Morphoware exhibition on biomimetic fashion revolution. And if you are interested to showcase your innovations with regards to biomimicry and your fashion senses or fashion products with regards to biomimicry, you can present them at our exhibition on 26th of September at Gap HQ Colombo 7. And we have facilitated everything. And you can get to know about all these things at from our website. And And also, I have to mention that the deadline for the abstract and full paper submissions for the Biomimicry 2025 conference has been extended. It's on 20th of August 2025, the deadline. And you can get more information with regards by scanning this QR code or by visiting the www.biomimicry.com website. And also, in this series of Nature Talks, the fifth webinar will be conducted on 31st of July 2025 with Professor Guttila Jayasinghe on nature intelligence. So these are the announcements that I was supposed to make. And dear sir, Dr. Angelo Karunarathne, thank you once again for this inspiring session. And thank you all for joining with us. And have a good night. Thank you all.
Good night, Sunny Malaysia.
Yes, thank you.